So let's discuss bottom balancing real quick. Now, this is something that I highly recommend if you're using lithium iron phosphate cells. Now, this is what we use. This is a prismatic lithium iron phosphate cell made by Cal. Now, these are very durable, very good performing cells. They don't have the highest energy density, but they are the safest chemistry on the planet today. They're safe, they're rugged, and they're reliable. We have not had a failure, not once. Now, the key, we don't use a BMS. We monitor them with instrumentation, as you'll see, and we bottom balance them. That's the key. Now, I had a Karmann Ghia that I drove 97,000 miles in just over 7 years, and those cells, there were 44 100 amp hour cells in that pack, and after 97,000 miles they were still all within a 100th of a volt of one another. So, I mean, it had been raced at the racetrack many times. It was a daily driver down the interstate running speeds 75 to 85 miles an hour routinely. It wasn't a babied pack. It was used, driven in the snow, autocrossed, proofs in the pudding. So to bottom balance these, we use a 4-step process, and we're going to measure the starting voltage. That's the voltage as received. In this particular one right here, in this whole batch, they were either 3.27 or 3.26, but most of them were 3.27. So that would be our starting voltage. And then using the method that I'm going to show you in just a moment, we're going to discharge it to 2.5 volts. And we're going to use some instrumentation that will monitor this so we don't have to sit there and watch it. And as soon as it hits 2.75 volts, it will disconnect that load. And we're going to discharge it at a 30 amp rate. Okay? As the voltage changes, the rate changes. It's an average at 30 amps. It basically goes from about 2.8 or 28 to 32 amps, but at an average rate of 30 amps. And you'll see what I'm talking about in a moment. And after that one is done, we disconnect it and we hook up the next cell and we do it. And this one is set aside. Now, once we've completed that, I always put a little dot on the top. And so this has been through the first 3 steps, because there's 3 dots, and I recorded the voltage at each step. So after it sits overnight, it's going to bounce back. Remember, we discharged it to 2.5. It's going to bounce back to somewhere in the neighborhood of 2.84. That's what that cell did. Okay? Step number 2, we're going to discharge it to 2.65 volts using the same process, which I'll show you in a moment. Again, after it's sat at least overnight, it'll bounce back to about 2.75 volts. And when this, we're gonna record that like I showed you a second ago each time, so you can see my starting voltage, and the 2.84 and the 2.77. The third step, I'm going to discharge to 2.73 volts, but this time I'm going to do it using an automotive headlamp, incandescent headlamp. And I'll show you that also in a moment. So these first two steps were done at this approximately 30 amp rate. This one's done at a very low rate. And the reason we do it at this lower rate, one, it's only going to take a minute or a few minutes to bring it down from the starting point on this one. It's 2.77. We're going to discharge it down to 2.73, and then it will bounce back to 2.75. The reason we do this consistent manner is we have control over the bounce back. We know where it's going to bounce back approximately, and all the cells should behave very similarly. If they don't, you might want to look at that cell. So then the fourth step is after they've sat and you've gone through all of them, and before you install them in the vehicle, you want to confirm that they are all truly at 2.75 volts. If they're not, do the fine tuning to make sure that they are. Okay, because that's our target. The whole objective of bottom balancing is to have all the cells be at 2.75 volts. That's a repeatable point on the discharge curve. So if you look at the discharge curve right there, it's getting pretty vertical. It's a point that we can replicate and know that all of our cells are at the exact same point voltage-wise and state of charge-wise. And so once we have done that, and they're all at 2.75 volts, they're installed in the vehicle, they're wired up in series, and then they are charged as a pack. So they have the same amount of energy go in, and they're in series, of course, so when you're driving, they're going to have the same amount of energy go out. They're all exactly the same. And because they're all exactly the same, and we're not top balancing them like a BMS wants to do, that's what if you were to discharge this pack all the way down, they're all going to go down together. So when you get down to that minimum voltage, which is 2.5 volts, and I don't recommend ever taking your pack that low, but if you did, this pack, they would all be there together. When you top balance, these cells don't all have identical capacity. So the one with the least capacity will discharge first, will completely discharge first. And you would have to monitor each individual cell so that when that one cell got down there, you could shut it off. We only have to monitor the pack. We don't have to worry about there being anything affecting our cells individually that would cause them to come out of balance or to cause us a problem. And I've seen a lot of battery packs be damaged by BMSs. There's a lot of opportunity for failure there. No BMS, no liability. And we've done this time and time and time again. It's the way I run my own vehicles. 97,000 miles on my daily driver, the orange Carnegie you've seen on our website. Proof's in the pudding. So this is the steps. We're going to track the steps and the voltage. You want to measure your starting voltage before you start the discharge procedure. Let's go over to the workbench and I'll show you exactly how we do the discharge procedure. So this is the process on how we do the first two steps. We're going to use a 12 volt auxiliary battery. And if you go to our YouTube channel, there's a video called The Economic Way to Bottom Balance LiFePO4 Cells. And it explains exactly how to do this part of it, how to program the JLD404, so forth. So if you buy one of our packages from us, this is included. And you're going to have a contactor, which is behind the cell here. Let me see if I can scoot it out here where you can see it. There's the contactor. These things are all in your vehicle. And so what we've got is the 12-volt battery is simply going to operate our JLD404 here. And this is programmed to shut this off when it reaches a certain discharge voltage. And when it does, this J2 light would come on and let you know that it's done. And so to reset it, we just turn off that switch right there. That just shuts off the 12 volts to the instrumentation. Okay. This just is a power switch between our instrumentation and the contactor, and that just allows me, when it's finished, I turn this off, disconnect the battery, the cell, and connect the next one, turn this back on, and then as soon as I flip this on, boom, the contactor is going to close and the discharge process starts. So the discharge process is very simple. We're using a 0.1 ohm resistor. This is 0.1 ohms, 300 watts. We have it attached to a big piece of aluminum as a heat sink because this thing will get very hot. We're putting, continuous, 30 amps through it. So starting at the positive of our cell here, we have two wires. One is a small wire that goes here so we can measure the voltage. We got one on the positive and negative. Then we got a heavier, a 10 gauge wire right here. It's going down to one side of our resistor. Goes through the resistor, comes out and goes to my contactor. Goes through the contactor and to the negative side here. So you can see when this contactor's on, we're just seeing this 0.1 ohm load, and that's discharging this cell. And when it gets to that 2.5 or the 2.65, whatever step we're on, we're going to program this accordingly. This will automatically shut off. So we don't have to be standing here watching it. You can be discharging this, doing something else. And so depending on the size of your cell, this is 180 amp hours. They typically are received with 50 to 60% state of charge. So at 50%, this would have 90 amp hours in it. And we're going to discharge it, and it's going to take, about 2.5 hours to do that, to get down to that 2.5. And then it's going to shut off. The second step is rather quick. It only takes minutes instead of hours. But we're going to go through and do all of the cells, however many you're using in your pack. Go through and do everything on step one. And then when they're all finished with step one, it's going to take you multiple days. So the first one's sat at least overnight. Reprogram the JLD404 and run through step two. Now, once you've completed those steps 1 and 2, we don't need this setup anymore. This was just the discharge at a faster rate. And after that, now we want to discharge this at a slower rate so that we have very little bounce back. So we showed you, originally we started off at 3.27 volts, discharge it to 2.5, remove the load, and it bounced back to 2.84. The higher the rate of the discharge, the greater the bounce will be. And so, yeah, it will discharge faster, but you're going to have bigger bounce. You're going to have to do multiple steps. So we've got it down to this 4-step process that everything's very controlled and repeatable. So bounce back to that 2.84 after step 1. Step 2, we took it down to 2.65. It bounced back after step 2 to 2.77. The goal is to take it to 2.5. To do that, we're going to use, like I said, just a standard old-fashioned automotive headlight. And we'll connect that to the cell. And this will only take, you know, a few minutes. I mean, it happens quick. So we would connect it, and we're going to put our voltmeter on there and watch that. And as soon as it gets down to 2.3, so we're going to watch it. It'll be, you know, 2.77, and it's going to drop down, and it'll get to 2.74. Now I'm paying attention, because I could be doing something else, glancing over at my meter. 2.74, now I'm really paying attention. As soon as it hits 2.73, boom, I disconnect, and it should bounce back to 2.75. And that's the goal. So for information on how to wire this up exactly in detail, how to program the JLD404 to do this, like I said, visit our other video on YouTube, The Economic Way to Bottom Balance LiFePO4 Cells. Now, the reason we call it economic is because these things are going to be used. This is from the car. This is going to be used in your instrumentation. This is going to be used in the vehicle. We typically use like the contactor for the heater is what we normally use. And then this you can get online. Just do a search. If you can't find one, contact us. We typically have a few in stock. So anyway, that's just an overview of bottom balancing the prismatic lithium iron phosphate cells. You can also do this with like the GBS lithium iron manganese phosphate cells. They respond a little bit differently in their balance and so forth. And again, this is a 180 amp hour cell, so the bounce on this one will be different than the bounce on a 100 amp hour cell. Not hugely, but they will, because this just got more capacity and has a greater capacity, you know, greater discharge capacity, rate of capacity, not just capacity of amp hours. And so they behave a little bit differently, but they're close. And so, you know, the time on that step 1 is going to be longer the larger the cell. If you're doing a 260 amp hour cell, it's going to take longer than a 100 amp hour cell because you're removing more energy. What we have is a positive, negative coming off our 12 volt battery, and they go to the positive, negative on the JLD404, the 12 volt positive, negative, and that's terminal 1 is positive, terminal 2 is negative. And all we've done is put a switch in line so that we can turn the JLD404 on or off. The other switch just allows us to turn off the relay, which basically is turning off the load. So that's kind of the 12 volt setup. The 12 volts is also going to operate our relay, and I'll show you that in a moment. The other connections to the JLD404 are the negative of the cell that we're doing right here, which is number 10, and then number 6, which is the positive. And then we're using pins 15 and 16 on this side, which just happen to be J2
normally closed. You could use 19 and 18, which are J1 normally closed, doesn't matter. So anyway, what we have is we have the positive lead, and this is sized for the load, and we're going to talk about what kind of current flow we have in a moment. But we have this line here goes to our resistor. Now this is a 0.1 ohm 300 watt resistor. This is our load for discharging this. That load's going to be dissipated in the form of heat, and this will get so hot as to not touch it. And we'll talk about how much power is being consumed in a moment also. So it goes through the load or the resistor. It's going through our relay and back to our battery. So there's your series circuit. Through the relay, through the resistor, to the battery. Okay? Now all the JLD404 is doing is the built-in relay in this case we're using J2, is switching this 40 amp relay that we have right here. It's a regular automotive relay we're using. Okay, so the 12 volt battery is providing power for our JLD404 and the power to activate our relay. This is simply being discharged through this resistor. Okay? So let's take a look at it in schematic form real quick. But anyway, here's a crude little drawing of what I just showed you. So you can see we have our lithium battery that we're discharging, goes through the relay, through our load, and back. And the 12 volts, there's our switch, it's powering the JLD404, and power goes through the relay, our secondary switch we had there, through the coil and back. So the JLD404 is simply turning this on and off, and we want it to do that so that when we discharge this to the minimum voltage that we want to discharge to, that the thing will shut off by itself. That's the whole purpose of this layout, is to discharge this battery automatically without us having to sit here and wait for it to hit a certain voltage. When it does, it's going to shut off all by itself. That load's going to shut off automatically. So let's talk about that. So what we have here is Ohm's law, which says that current equals voltage divided by resistance. And we're also going to talk about the power. And power is volts times amps. So, how many amps do we have going through the wires? And you know, how did we choose the size of wire? Well, we took our 3.3 volts, which is going to be the maximum that we're going to have in this project here, and we're dividing it by the 0.1 ohms of our load, our resistor, and that gives us 33 amps. That's the maximum current that we'll be drawing through this circuit here. And so if we then take the voltage, the 3.3 volts, times that current, it tells us that we're going to be consuming or putting out 108.9 watts. So 100.89 watts is enough that this resistor is going to get hot enough that you don't want to be laying your hand on it. The minimum we're going to take this down to is 2.5 volts. So that's where we're going to shut off. So when we shut off, 2.5 volts divided by 0.1 ohms would be 25 amps. And so 2.5 volts times 25 amps would be 62.5 watts. Okay? So that's how we, you know, those are the figures that we used for sizing the wire and so forth. Well, the next thing that people will want to know is how do we program the JLD404 to do this? Well, let's first take a look at the back. We're at 3.3 volts, so we're running on the scale on number 6. And number 6 is the 100 volt scale. So you got 500 and 100. So we're running off that, and then number 10 here was the common. So that's our negative, this is our positive. So now let's take a look at programming the JLD404. Well, the base programming, we need to enter code 36. So there's 3, 6. And we're not dealing with a shunt in this. All we're worried about is voltage, so we can skip through all of those. So now we have the voltage settings. And so we're set on the 100 volt setting. Okay, that's what it reads when we have 0 volts. That's what it reads. And that's what it would read if we had full scale. And this is the decimal point. We're only using 1. Okay, so that's setting up the meter. Now, to set up the relay, we're going to enter 0001, and that takes us to the relays. We have it set up on J2, so I'm going to skip through all the J1 related ones. On J2, we're using volts. Okay, you can use amp hours, amps, or volts. We, of course, we're using volts. Then this is our high or upper setting, and we have that set at 3.1 volts for this demonstration. That's not where you would normally have it set. Normally we would set this at 2.5. And then we have this set at 3.5 because we're not ever going to reach there. That makes sure this thing is on during our entire discharge setup. So, I'm going to turn this on. How this is set up is because we're on the normally closed settings, is that power is going to come from our 12 volt supply. It's going to go through J2, which is normally closed right now, and it's in the off position. When J2 is latched, this will come on, and it'll open, and it'll shut this off. And it's set to come on at 3.1 volts. So we don't have to sit here and wait for it to do all that. I know that it's going to do that fairly soon now. So as soon as I turn on this switch over here, you zoom out a little bit. So as soon as I turn on this switch, our relay is going to close. We're going to have a load, and this will drop. And we'll see how long it takes here, so you might have to be patient. And I can feel it. I don't know if you could hear it, but anyway, this is on. This is going to heat up. I mean, it takes a minute or two for this to get nice and hot, but over time it does. We just have it on this piece of scrap that's nice and thick aluminum. Just acts as a little bit of a heat sink, but most of this heat's just dissipated to the air. This gives us a base to lay things on and keep it from moving around. And you want it on something because it does get hot. You don't want to mount this on a piece of wood or something that will melt or eventually char or burn or whatever. So on a piece of aluminum, we don't have to worry about it. It protects our workbench from this resistor. So what will happen is when this gets down to 3.1 volts, when the battery does, this calb cell, then J1 will come on, which will, open. There it goes. Now it'll stay open, so I don't have to be around. This shut off at 3.1, and even though the voltage bounced back up after the load was removed, it's still not going to come back on and further deplete my cell. So that's all there is to it. So what I'm going to do is I'll reset it by shutting it off. That'll let that relay unlatch. Turn it back on. We're at 3.2 volts. We'll reconnect our load. And it should repeat again. So you got to watch fast. It'll go down to 3.1. You'll see the J2 light come on. It's right there. So there you had it. The 3.1 is pretty quick. As soon as you drop this load off of there, that close to 100-watt load, it jumps back to 3.2 pretty quick. And that's just for demonstration purposes. I have them set real close. Normally, like I said, we would have the one setting set at 2.5 volts.